So before we look at pH as a scale, let's look at the scale we made with colors. I mean, our cabbage juice indicator is a type of acid-base scale, and it uses not pH numbers, but it uses colors for acidity. And they're not all here. You saw them in the other video probably, but at the red end we have very acidic compounds, acidic solutions, I should say. And on this side we have bases, and cabbage base indicator that is in neutral, in water without, that isn't acid or base, is a purplish color. And of course we made it from, I made this from purple, or usually called red cabbage. I don't know why, I've never seen it red, but, and in the other video I showed you how to make that yourself. So this is a type of scale as well. And it's useful, but it's a little hard to work with in terms of some other kinds of science and sharing. So numbers are often easier. As science sort of developed, we learned a lot more about atoms and substances and materials, and certainly, and then we started to make models for things like these stick and ball models that we used for atoms. You've probably seen those before. In my hand is a red model of an oxygen atom. It's not, oxygen atoms aren't really red, of course, but it's a okay model for one, and it's pretty big, and it's got a hole in it that we can stick in and add a white oxygen. By add, I mean there's a bond here. So this stick, it's plastic, but it represents a force that holds the hydrogen to the larger oxygen. And in fact, not a bad model. I mean, oxygen is much bigger than a hydrogen atom. So there we go. And you already know the chemical formula for this. Even if you haven't taken chemistry yet, you know that this is H2O, don't you? That's what water is. H2, because there's 2 H's. So there's a subscript 2, and there's 1 O. I guess we could have said H2O1, but that's sort of a waste of a breath, isn't it? Why should we say 1? Let's just assume that the 1 is there. H2O. And water, of course, is almost all H2O. And what you may not know is there's a little bit of some free ions in there. In other words, an atom of hydrogen in this case that is not yet attached to anything else. And it's got a slight positive charge, and it's sort of just floating around in a whole lot more water, which is made mostly of H2O. So it turns out that one way to measure and to scale pH is to look for how much free hydrogen ions there are in the liquid. And in this case, there's a ratio between how, for every hydrogen, how much water molecule is there. So the numbers are big, and this is where that logarithm and the formulas come into play. Because in pure water, like in the purple jar, for every 1 hydrogen, there are 10 million water molecules. It's a big ratio, but it is present enough to be counted. 1 to 10 million. And that is why we turn to other ways of writing some numbers, because 10 million, that's a pretty hard number to write. And so we can use logarithms to bring it down. So the most common formula for pH, which I mentioned before, I think, is the negative of the log of the concentration or ratio of hydrogens to water in a solution. And crazy. Why are we using logs? What good is that, right? So, well, interestingly, it solves some problems that scaling and measurement produce when we look at acids and bases, which in some ways didn't come up with measuring other things like temperature. So let me show you an example of that. Let's go back to water. So water has one hydrogen, put that in parentheses, for every 10 million waters, H2O. And that is a lot of waters for every one hydrogen, isn't it? And so certainly dealing as a ratio or fraction, that'd be sort of a difficult thing every time we want to talk about the acidity of water and say, well, you know, it's 1 over 10 million. And I suppose we could say that it's a one, well, let's do the math there, that would be 1/10,000,000th. We could say that also that is 1/10,000,000th. So those are equivalents. But that is also quite cumbersome, isn't it? And so we can use what's called a log base 10. And log base 10 is in many ways the inverse of exponents that you might have used, like 10 to some power. And except what it is what is it that we have to raise? What exponent would we have to raise? In this case 10, because it's a log base 10, to in order to get this number. And then we can use that as an equivalent for that number. So we'll take a look right here. Let's do that on my calculator here. And I think what I'll do is enlarge it and center it here for you a little better so you can see it. And let's do the full formula here. So we're going to take 1 and divide it by 10 million. I think I've done that, and that equals 1/10,000,000th. That makes sense. And then we're going to look for the button that says log or log 10. If there's no 10, that's usually the default. You don't want to put, it's the most common log, but we don't want to don't use ln, which stands for natural log. That's not the same thing. But look at that. We have a -7. And remember the formula is we take the negative of the log of the ratio, and a negative of a negative number is a positive number. So the pH of water is in fact 7, right? And so all of these things, in a way, are equivalent, at least if we're talking about pH, right? And H should be capitalized for the element hydrogen. And what the P is interesting. There's debate about what the P is for. And you'll find different things written about it. I think of it as power and, you know, the strength of hydrogen. And then I think, oh no, it's about like powers of 10, right? Like in a log or an exponent. But so either way you think about the P is fine. But the P is usually small, is always small, and the H is always big as the atomic symbol for hydrogen. And so you can see right away I've got a number, kind of more like a number in a temperature scale that I can manipulate, that I can write down, that I can graph, maybe compare to something. And let's compare to something right now. Let's look at another substance. Let's do lemon juice. Pure lemon juice has about 1 hydrogen, and this is what's also remarkable, for every 100 water molecules. Wow. So this is another problem with pH. There are so many more hydrogens, as in hydrogen ions, in lemon juice than water. 10 million to 100, that's 100,000 more per water molecule. And so how can we get equivalent to that, right? And of course, it is the same thing as 1/100th, right? but what is the pH going to look like, right? I meant to have another right there. And so let's do that math. Let's do that. And I'll clear my calculator, and I think I'll make it bigger again for us so you can see it. And let's take 1 part hydrogen per 100 waters equals, you know, as I pointed out, 1/100th of something. And then we'll take the log of that. 2. And again, the 2 is negative, but our formula says, no, we're going to take the negative of this log, and the negative of -2 number, right, is in fact 2. So now we've been able to deal with, I'll make this, we've been able to deal with some very cumbersome numbers and turn them into some pretty simple ones, right? We can say that the pH of water is 7, the pH of concentrated undiluted lemon juice is 2, and even though they're very, very different, we can put them on a scale. But remember that every number between 7 and 2, by the way, is 10 times more acidic. So 6 is 10 times more acidic than 7. 5, 10 times again. And 4, 10 times again. And 3, 10 times again. And so we're able to put a huge difference between the number of hydrogens, the acidity, onto a single scale by not using a linear scale. So a logarithmic scale like pH is not linear. And if we had used a linear scale, I mean, think about it would be huge. It'd be impossible to draw, to write on. So that's also an example of why log works so well for us here. And I think in total, I think that should help you understand pH, why the number goes down. And it's going down because we're taking the logarithm in base 10. And another advantage there being that we're able to deal with very large differences between our numbers. Let's go the other way. Let's put some neutral pH solution in the middle. And remember, that's going to be about pH 7. See if I can mark that with a marker. So pH 7 is in the middle, and acids can, as we just saw, we get a lower pH and increase acid, and we can go all the way down or very close to 0. And bases, we can see the pH go all the way up to 14. And that's the range of a strong base down to a strong acid. And but I think what I'd like to do is let's push this liquid into the base category. And right now we're still neutral. So I do have, this is actually a compound of ammonia. And let's see what happens when I add that compound to the water, which is showing as neutral in purple right now. Look at that. That's a beautiful kind of bluish color and blue-green color. And we definitely have a shift. If you were to look at the scale for cabbage juice indicator, you would see that this color indicates a more basic substance than the original purple color of the cabbage. So what's going on in solution? Well, we still have plenty of water, right? So there's water present, and that's nothing new, so that'll stay. And we have probably some hydrogen still hanging out. But originally we had that ratio of 10 million waters for every 1 hydrogen. But when I've added this compound, the ammonia compound starts to tie up and remove these free hydrogens and binds them up in other ways. And in fact, it's so strong that it sometimes actually just deconstructs a H2O water molecule and grabs one of those hydrogens. And so you end up with, in a strong base, water, of course, it's still a solution, a little bit of hydrogen, unless it's all the way over to 14. But you also end up with something called hydroxy, which is a sort of this molecule that is, well, what is it? It's an HO. It's sort of a water missing one of its, not sort of, it's a water missing one of its oxygens. It turns it into a very different molecule, very different chemical. And so bases in solution, water, not a lot of hydrogen ions, and even some hydroxy. And that's what happens at sort of the molecular atomic level. And let's take a look at what we might be able to look at in terms of the math involved in calculating pH. So I think I'm going to go back to my larger view there, and I'm going to make some estimates here on what I think is going on in terms of a different pH. So let's take the log of one hydrogen ion. There's going to be some in there. By the way, it's not all the way even to the yellow yet, so it's not completely basic. And then again, it's 1 per, so I can use the division symbol. But I'm going to really push these numbers up. So we were at 10 million waters. I think as a ratio, I think there's even fewer now. So it's going to be 1 to every 1 billion. Let's do 1 billion. I think I did that right. A pH of 9. A pH of 9. And can you imagine, though, if we had to deal with not using a logarithmic scale? So I can just say, well, that's pH 9. Let's take a look at it again. That's a pH 9. And much better than saying, that is 1 to 1 billionth of, in terms of the ratio between hydrogen and water molecules. So there's another example there of why we might want to do that. We can manipulate the numbers that are smaller, and we can deal with huge changes there, right? A huge number of differences in between even 10 million and 1 billion. And yet through using logs, in this case negative logs, because we can kind of handle that, graph it, keep track of things a little better. So overall, I hope that helps. A couple of things I think you want to remember is that, yes, when pH goes up in number, it becomes more basic. And when the pH number goes down, it becomes more acidic. And that water is neutral and a pH of 7. I think that's maybe the one thing I've memorized. I just think of lucky 7 as pH neutral. And overall, I think that I've enjoyed looking into acids and bases. I hope you did a little bit. And if you'd like to make your own cabbage juice pH indicator, check out my other video. And I think if you do, you'll find your investigations can reveal some interesting aspects of our world and even some pretty cool math. Okay, bye-bye.